Okay, we've covered a lot of content dealing with chemistry, which is, of course, one of the main physical sciences. For the remainder of the course, we're going to look at some other physical science as well, particularly geology and meteorology. And so we're going to start by shifting from chemistry to geology. And in this chapter, in specifics, we're going to look at rocks and minerals. Now, one thing that is startling to realize is that when you look at the entire Earth, 98% of its mass is made up of just 8 elements. Now, of course, different elements can combine into more complicated chemical compounds, but when you reduce everything to its fundamental building blocks, only 8 elements make up 90% of the Earth's mass. And here you see a pie chart showing the biggest contributor to the Earth's mass is iron, and then oxygen, silicon, magnesium, and several others. You can read them on the chart here: nickel, calcium, aluminum, sodium. These make up a much smaller percentage. And then all the other elements combined make up only 1.9%. Less than 2% of the Earth's mass is made up of things like gold or silver or the other things that we've talked about in the periodic table. Now, we know the Earth formed about 4.5 billion years ago, and it formed out of the rocky debris from the early solar system. Gravity attracted all of these masses together, and they slammed together and joined together. And as they slammed together, those collisions generated a lot of heat, and it increased the mass as these different masses in the early solar system started clumping together into the early planets. And as they got bigger, their gravity got stronger, so they could attract more matter, more mass onto them. But constantly these things were crashing together, releasing huge amounts of heat. And so very early in the Earth's existence, there was so much heat that essentially the entire ball of the planet was liquid. It was molten. And if you have a molten surface, a liquid surface, what happens to the heavier things? The heavier liquids are going to all sink down towards the center. And that's exactly what happened. The iron and the heavier elements, they tended to sink down towards the center and coalesce. And so the Earth's center, the outer core and the inner core, are very, very iron rich because a lot of the iron and heavier elements sunk down into that core. Now, for the same reason, as they sank inward, the lighter elements got pushed upwards towards the Earth's surface. And so when you look at the sections of the Earth, you can see that the denser parts of the Earth are at the center and the less dense parts are towards the surface. Now, you can see the sort of sections of the Earth that we know exist. And so there is the Earth's crust, which is the part we live on. And then once you penetrate through the Earth's crust, you get into a rocky region called the mantle. And then as you travel inward further towards the center of the Earth, you get to the Earth's core. Now, there's a inner core, which is the very, very center, and then outside the inner core is a liquid outer core. And so we know that there's this sort of liquid outer core and then this very, very dense solid inner core. Now, the core, as we said, is primarily composed of iron. There are some other heavier elements like nickel in there, but mainly it's iron. The mantle is a region that's made up mostly of silicate materials, silicate-based rocks, and then surrounding it all is this very thin layer which we call the Earth's crust, and it's made up of various other lighter compounds. Now here we see a schematic showing the makeup of the Earth's crust. 70% of it are made up of oxygen and silicon, and of course you can see aluminum, iron, other elements make up other parts of the Earth's crust. But silicon and oxygen are by far the most abundant elements in the Earth's crust. A lot of it in the form of what's called silicon dioxide. We know that's SiO2. That's called silica, and that gives you sort of an insight into the composition of the various levels of the Earth. Next, we want to talk about rocks and minerals. Specifically, let's talk about minerals. Now, minerals are naturally occurring substances that have distinctive chemical and physical properties. They have distinctive compositions and atomic structures. Rocks, on the other hand, are generally made up of multiple minerals that have been mixed together through some geological process where they've been mixed up and combined. Now, when we're talking about minerals, they're generally things that are naturally occurring. That is, they're not manufactured in a lab. They're formed naturally in nature through natural processes of the earth. And generally, they are crystalline solids. And so a crystal is a solid that has atoms that are arranged in regular patterns. So the atoms might be arranged in little boxes or little pyramids or other shapes. And because they have these regular shapes like boxes or pyramids or whatever, that means they have an order to them. There is a repeating arrangement of atoms or ions or molecules. They also have very specific chemical compositions. Now, there can be slight variations, but overall, over the whole substance, you'll see the same chemical composition from one mineral to another. And generally, they're inorganic. Of course, you probably know the word organic. We talk about things like organic foods. Organic generally refers to living things. And so inorganic things are things that are not living. And so these rocks generally come from inorganic or non-living sources. So how do we classify different minerals? We classify them by their properties, specifically their chemical composition. That's the elements and chemical compounds that make them up. And so each mineral type has the same basic chemical composition. We also classify them by their crystal structure. Like, for example, if their atoms and molecules are arranged in pyramids, that would be one kind of crystal. If they're arranged in little boxes, that would be another kind of structure. But each mineral type has the same geometric arrangement of atoms, whether it be a box or a pyramid or hexagons or whatever other shape. There are different possibilities. And so we can look at how the atoms or molecules are arranged, what shapes they fall into, and we can classify different minerals by which types of shapes their atoms form. Now, way back at the beginning of this class, we talked about the difference between chemical properties and physical properties. We can also talk about minerals in terms of their physical properties, and that can include things like their crystal form, how hard they are, how they tend to cleave or split. That's called cleavage and fracture. We can talk about their color, their density, etc. Now, when we look at these, we can say that crystallization, this is how crystals are formed, it's the formation and growth of a solid from a liquid or a gas. And so you might have some material that's liquid, and as it cools down, we know it's going to change from a liquid into a solid. And as it changes from a liquid into a solid, the atoms line up in these different crystalline arrangements. And so they form in specific chemical compositions and specific geometric arrangements. The combination of chemical composition and the arrangement of atoms in an internal structure makes each mineral unique, and many minerals are identifiable by their crystal form. If you've ever written with a pencil, you know the part that actually gets left on the page, we call that the pencil lead, but it's actually not lead. It's not the chemical element lead. It's graphite, which is an arrangement of carbon atoms. And so if the carbon atoms are arranged a certain way, they form into graphite. Now, you might know that another way that carbon atoms can be arranged is into what we call diamonds. Diamonds are very different in their structure from graphite. You could never make a pencil out of diamonds because the carbon in the diamond wouldn't flake off in the same way on the page. The point is that you can have atoms arranged into different configurations that have very different properties. And so that's the same with crystals. So the first thing that determines the mineral properties are going to be what atoms, what molecules make up the crystal. And then the second thing is how those crystals form, what shapes do they take, etc. So why do they take different shapes? Well, that has to do with the internal atomic arrangement, and that's going to be determined things by the charge of the ions involved or on the atoms, the size, the way that they pack together, and also the conditions in which the crystal grows can affect the form. What's the temperature under which they formed? What was the pressure under which they formed? How much space do they have to form? These are the kinds of things that can affect the types of shapes that are formed. And the other thing to know is that well-formed minerals are very rare in nature. Most minerals grow in cramped, confined spaces, and that affects how they form. So let's look at our example of graphite versus diamond, where we have both graphite and diamond are made out of carbon. So it's made out of the same stuff, but the arrangement of the atoms is very different, and so that leads to different types of minerals. In diamonds, the atoms are arranged in a three-dimensional structure which is very strongly bound to each other and very rigid. That's what gives diamonds its strength, their strength. Now, graphite, the atoms are arranged more into like sheets. And so there's a very strong bond in two dimensions, but in the third dimension, the different layers are only weakly bonded to one another. And so you can see here in this picture, you can see it's like sheet laying on top of sheet, laying on top of sheet. If you apply a sideways force, you can actually separate those sheets. That's how a pencil works, how you are dragging the pencil across the page. These sheets are basically flaking off and being left behind on the page. With a diamond, you can't do that because the atoms are all so strongly bound together. And so what you end up with is carbon forming very, very different types of structures in its different forms. Minerals that are made up of the same material but that have different structures and different properties, those are called polymorphs. And so you have a different crystal structure and that gives the minerals different properties, even though they're made of the same stuff. Another property that is used to characterize minerals is its hardness. And hardness is the resistance of a mineral to being scratched. And so hardness is dependent on the strength of a mineral's chemical bonds, and that bond strength is determined by ionic charge, by atom or ion size, and by packing, how they pack together. We use what's called the Mohs scale to compare the hardness of different materials. And so you may have heard that diamond is, for example, one of the hardest materials, the hardest minerals. And if you take something like sapphire, sapphire is another very hard mineral. Generally speaking, you wouldn't be able to scratch a diamond with a piece of sapphire, but you would be able to scratch a piece of sapphire with a diamond because diamond is harder. Or maybe another way that minerals are characterized is by their tendency to undergo cleavage and fracture. Now, cleavage is the property of a mineral breaking along planes of weakness. And so planes of weakness are determined by the crystal structure and bond strength. Like we talked about the planes of the carbon atoms in graphite being sheared off and left behind. Fracture occurs in minerals where the bond strength is generally the same in all directions, but there's just a split or a break. And so, generally speaking, minerals that fracture do not exhibit cleavage because they would tend to cleave apart rather than break apart through a fracture. Now, one of the other things that historically have been used to characterize minerals is their color, but that's not the best way to characterize minerals because chemical impurities can change a mineral's color. And so a mineral can occur in many different color variations or even be colorless. Another characteristic property of minerals is their density. And of course, density is the ratio of mass to volume. So if you take an object's mass and you divide it by its volume or its size, that gives you its density. And in simple terms, the density is how heavy a mineral feels for its size. So let's check our understanding here. Physical properties of a mineral are predominantly related to what? A, the external conditions of temperature, pressure, and the amount of space available for growth. Okay, we've talked about that. The chemical composition and the internal arrangement of the atoms that make up the mineral. Well, we've really talked about that. The crystal form, hardness, cleavage, fracture, and density, or all of the above. Now, we've talked about these, but things like crystal form, hardness, cleavage, fracture, that all comes from the chemical composition and the arrangement of atoms. And so we know that this one seems to be the important one here. The external conditions of temperature, pressure, and growth, that's what causes the chemical composition, causes the internal arrangement of atoms from the chemical composition, but not a separate thing. So it looks like our answer has got to be B. The chemical composition and the internal arrangement of the atoms, that is what predominantly determines the physical properties of a mineral. Now, what about the color of a mineral? What is that predominantly related to? Is it related to the chemical composition, the internal arrangement of atoms, its luster, or the temperature and pressure conditions at the time of crystallization? It actually is A, the chemical composition. And we know that if we have chemical impurities introduced into our mineral that can change its color, but it's the chemical composition that really determines the color of the mineral. So our answer is A, chemical composition. Now, there are just two classifications of minerals. They're what are called silicate minerals and non-silicate minerals. Silicate minerals make up 90% of the Earth's crust. Now, silicate materials are made up of silicon and oxygen, but sometimes they can include other elements such as aluminum or magnesium or iron, etc. And all silicate minerals have the same fundamental structure of atoms, the silicate tetrahedron. That is the official name, but you can see I've already mentioned this shape earlier. It's like a little pyramid, right? So anyway, you can see that you have this atom at the center, and then you have this sort of pyramid-like arrangement of atoms surrounding it, the red ones. Hopefully you can kind of see that that's the shape of a pyramid. But the official term, of course, is not pyramid, but it's actually a tetrahedron, and specifically a silicate tetrahedron, since we're talking about a silicate compound. We can further define silicate compounds into what are called ferromagnesian silicates. Those are silicate compounds that contain iron and or magnesium. And these arrangements of atoms tend to have very high densities, and they tend to be very darkly colored. The other class is what we call non-ferromagnesian silicates, and those have no iron or magnesium content, and they tend to have low density and they're lighter in color. So we can look at some of the different types of non-silicate materials. Those are materials that don't contain silicate, and those materials make up about 8% of the Earth's crust, and those include carbonate materials, which include things like calcite and dolomite, oxide materials, sulfide materials. What do you think carbonate means? Well, I see the word carbon in it, so it suggests to me that a carbonate material has something to do with carbon. And actually, a carbonate is a salt of something called carbonic acid, which is H2CO3. And of course, you can see right there, there's carbon in there. What about the next on the list? Oxide minerals. Guess what? Those are minerals that contain oxygen. Some of the examples are listed here. I'm not going to go through all of these. I don't expect you to memorize these. But the main thing is that you can see that there are non-silicate minerals and there are different classifications of them. You can see sulfide and sulfate. That's kind of interesting. What does that suggest? It might suggest that both of these involve sulfur in some way. And in fact, they do. A sulfide is a compound of sulfur with a metal typically, whereas sulfate involves sulfuric acid. But you don't need to know these specific details. Just know that there are different ways of classifying these compounds. So let's check our understanding. The silicates are the most common and abundant mineral group because silicon and oxygen are the hardest elements on the Earth's surface. I don't think that makes sense. Oxygen is typically a gas. It's not a hard surface. The two most abundant elements in the Earth's crust, I think we've seen that already. These other two don't really have anything to do with it, why they're the most common. So I think our answer is going to be B. It is the two most abundant elements in the Earth's crust. Now let's talk about how minerals form, the formation of minerals. Minerals form by a process called crystallization. Minerals crystallize from two primary sources. There's molten rock, which we call magma, and then there are basically water solutions, where minerals are dissolved in water and they come out of those solutions and form crystals. And we can look at some general rules. Minerals crystallize systematically based on their respective melting points. So the first minerals to crystallize from a magma are those with the highest melting point and the lowest amount of silica. And conversely, the last minerals to crystallize from a magma are those with lower melting points and higher amounts of silica. So what does that mean? Let's say you had some magma that was at 5,000 degrees. And as it starts to cool, you might find that some of the stuff that makes up that magma melts or solidifies at 3,000 degrees. And so as it cools below 3,000 degrees, that stuff is going to solidify first. And then you'll have these little bits of solid in the liquid parts that are remaining. As it continues to cool, the other things, maybe there's some things that become solid at 2,000 degrees. And so that would become solid as it cools below 2,000 degrees. And so the ones with the highest melting temperature, they're the ones that are going to be converted to solid first. That's all that this is saying. And it turns out that this also tracks with the amount of silicon content that they have. So these are kind of the things that we can look for to see what minerals are going to crystallize first and which ones will crystallize later. We can look at their silica content or their melting temperatures. Now, another way that crystallization can happen is through crystallization of a solution. Now, we've talked about, for example, previously we talked about how if you have a solution, like I could put water here into this container, and then I could start dumping sugar in it, and the sugar is going to dissolve, and the more sugar I put, the more it dissolves, but eventually I get to a point where the solution is saturated. So you can't put any more sugar into the water. But we also talked about how if I raise the temperature, I can put more sugar into the solution, more will dissolve. And if I then cool it down, that solution becomes super saturated. And if I disturb that solution somehow, the excess sugar that's dissolved in that water can crystallize and it'll come out of the solution. This is the kind of process that we're talking about. So we have water solutions that have become chemically saturated. That means you've dissolved as much stuff in them as you possibly can, and something changes the conditions of that water, so some of those dissolved materials will come out of the solution, and when they do, they form into crystals. Very often, if you're talking about ore deposits, like iron ore or something like that, these occur. They end up getting, because of these solutions can flow into cracks and things, and that is why you often find these kinds of deposits deposited into cracks or embedded within a rock itself. Now, water solutions can precipitate chemical sediments such as carbonates and evaporates. For chemical sediments, solubility rather than melting point determines which minerals will form first. So when we're talking about crystals forming out of magma, where the magma is cooling down, what determines which things crystallize first is what their melting point is. But when we're talking about crystallization coming out of a solution, the solubility is the important factor. So which materials are more easily dissolved or less easily dissolved. And so the low solubility minerals, they're the ones that precipitate first. That means they come out of the solution. And the high solubility minerals, they precipitate last. And so that's just the rule of thumb for how to determine which materials are going to crystallize out of a solution first or last. So we can look at sort of a quick little quiz to check our understanding. In the crystallization of chemical sediments from water solution, low solubility minerals precipitate first. Why? Because A, they dissolve more easily. B, they're more susceptible to being dissolved. C, they're not as easily dissolved. Or D, they're infinitely soluble. Well, let's look at that. They dissolve more easily. They're more susceptible to being dissolved. Those are kind of two saying the same thing. So that makes me think it's not them. But we also know that low solubility minerals precipitate first because they're not easily dissolved. That was the whole point. And so we can rule out A and B. We can say C looks like a winner. We know D is not going to make any sense. What does it mean to be infinitely soluble? We know that eventually solutions will be filled up. So clearly the answer is going to have to be C. They're not easily dissolved. And this is a good stopping point, so we'll finish the lecture here and we'll continue on in the next video.